Okay, so in the second part of last week's class, we were asked to generate some data set that is actually the same as in Mockstad and the co-authors papers. And here's just to remind you what we do, or what we did last time. We have an instrument, Z, which is discrete, 0, 1, and takes values 0, 1, and 2 with probabilities 0.5, 0.4, and 0.1. We have our U variable that is related to the probability of treatment. And so this probability of treatment is enters this equation. So we have this condition that some linear function of z's has to be greater than u, and then the treatment status in the observation is 1, otherwise it's 0. And u is distributed uniformly, and so basically u is the probability of treatment. Sorry, this is the probability of treatment on the left-hand side, and to make sure that this is the probability, these probabilities that we have in comments, we use this u as a uniformly distributed variable. It's kind of related to resistance to treatment. And our potential outcomes also depend on u. So we have the m0 function, which is the probability that y takes the value 0, and then 1, the probability that y takes value 1. They're quadratic. We use this weird polynomial, but it's just a quadratic function. And this is the graph of the difference between m0 and m1. So this is the true marginal treatment effect depending on u. And it's slightly curved quadratic line. And of course, once we have these potential outcomes y0 and y1, whose probabilities? So this is y0 when there is no treatment, y1 when there is treatment, and the probability of them being 1 are m0s and m1s, or the expected values. But since it's a binary outcome, it's the same as probabilities. And we make sure that we generate these values using these probabilities from this vector. That's the setup. And again, we've seen this already. We try OLS. Yeah, and get this estimate 0.25. We try two-stage least squares and get a smaller estimate 0.07. But the true average treatment effect is, of course, the difference between our expected potential outcomes, and it's 0.0667 and so on. So we see that OLS grossly overestimates the effect, and our two-stage least squares slightly overestimates the effect. The question is, why is this the case? Well, if we look at our equation, then for an observation to be a complier, and that's what obviously the two-stage least squares is going to give us in this case, and we have two sorts of compliers, those that comply when z is equal to 1, and those who comply when z is equal to 2. We can think of these variables as two instruments. And if z is 0, then treatment status will be 1 if u is smaller than 0.35. And those are always takers. So, and we see in our treatment effect curve that the highest value of the treatment effect is actually for lowest values of u. So these are all always takers. And of course, if u is greater than 0.7, this part of the graph, then we will have never takers. And for never takers, the treatment effect is the lowest. And we have two values of, so two types of compliers, the ones for the which are shifted by the first instrument when z is equal to 1. And those are compliers when, so the observation is a complier if u is between 0.35 and 0.6. And the true late for these compliers is 0.79. And then the second instrument when z is equal to 2, the compliers are those observations for which u is between 0.6 and 0.7. And for them, the true late is 0.04. And so the thing that our IV regression estimated using two-stage least squares gets is a weighted average between the two effects for compliers. And actually, the share of compliers of type 2 is slightly over 5%. And that's because, obviously, well, first of all, the distance between 0.6 and 0.7 is smaller than between 0.35 and 0.6. And of course, u is uniformly distributed, so that would directly affect the number of compliers of the second type. But also the probability is that z is equal to 2 is just 0.1, as opposed to the probability of it being equal to 1 of 0.4. And so we have pretty few compliers of type 2. Most of them are of type 1, and we see that the IV gets this estimate pretty, or this late pretty accurately. Yeah, and I wrote the text why both of them are upward biased. Well, not biased if we talk about the two-stage least squares, but it's higher than the average treatment effect. And now we're going to try to estimate the average treatment effect using our margin treatment effect methodology. And we know that these functions are actually quadratic. And we know that the propensity score does actually have this form. So, and we include an exhaustive specification in our moments argument. So we will have all the possible moments. All the variables are binary. So we're going to do this just the same as we did in the first part of the problem set. And once we do that, we get this estimate. And in this case, it's pretty low. I think last week I got something pretty high, and it turns out that all those weird values were due to the sampling error. So last time I tried to generate a relatively small sample. This time, well, in this particular version, it's 500,000 observations, but I played with it and used different numbers of observations. For example, if we go to 1 million observations, then the values, these values will be closer to the true value. And as we can see, these, or if you try different numbers of observations, you will see that these values are pretty sensitive to the number of observations, which means that the variance of our estimates is pretty high. And we would, of course, notice that if we did the proper bootstrap, and as in this example, which I didn't run because it takes a lot of time. But if you're willing to wait a bit while the computer runs all the bootstrap simulations, you will see actually the confidence interval of all these estimates. And it turns out they're going to be pretty broad, and that's what puzzled me last time, specifically in the fifth problem, but in this one too. Now we're asked in the question to try different specifications for our M0 and M1 functions. If we add a third term, then of course we don't have point identification anymore, and we get this kind of bounds, these kinds of bounds between minus 0.03 and 0.2 plus 0.23. And again, this is not informative, and this is yet another illustration of the trade-off between flexibility of our specification and our estimates being informative. Now, just to remind you, the true value is 0.066, I think. This is one. Okay, so that is what we did. We can actually plot. So I'm plotting the better result, not this crazy result, but well, not crazy, but not this less informative result, but a more informative result. And what I do here, I plot, and we have already seen it before for a different data set, but but now we have the true values of our M0 and M1 functions. So these are the estimated M0 and 1, and I plot them together with the true values. The true value is in red, the estimated value is in blue. And we see that they're kind of close, but not really that close. And this goes for the upper bound of our parameters. And we can do the same for M1. Again, we see the difference, and that's why our bounds are not actually the true value. But it turns out that sampling error actually affects the slope of these estimated curves pretty wildly in small samples. Finally, we can say that we want our marginal treatment effect function to be decreasing, and adding this argument, and we get an estimate that is actually pretty close to the true value, 0.06. And again, this gives us another illustration of if we impose additional restrictions, so make more assumptions, our estimates become more informative, and actually in this case closer to the true value. And we can plot the curves that look pretty similar. Yeah, so this is basically what I wanted to, the point I wanted to make with this exercise, and with this particular, returning to this exercise, is that sample size matters. If you have a small sample, this method is going to be probably very imprecise. And if we look at the IV, it actually doesn't do that. I mean, the two-stage least squares, it doesn't do that bad a job here. So it's a little bit over the true average treatment effect. But yeah, the thing is, it estimates a different thing. It estimates late. But in this particular case, what the kind of variation we get using our marginal treatment effect estimations from, so if we don't include the monotonicity assumption, it's 0.03. If we include it, it's 0.06. It's kind of not very helpful, unfortunately. I guess the main takeaway could be that if we have a discrete instrument, then there's not that much we can do about getting away from late. And last time We've also seen how we can extrapolate lates using this so-called generalized lates. I should add it to the notebook. Yeah, so I'll add that to the notebook. But basically, if we replace the target to gen late, we can specify the values of u for which we can calculate the late, because here the lates we can calculate is, of course, for using the two-stage least squares. We can calculate these two lates. Yeah, so from yeah, so this is the effect when z is moving from 0 to 1, and this is the effect when z is moving from z is changing from 0 to 2, and that shifts the treatment status. And this is when z shifts from 0 to 1, and that's changes from 0 to 1, and that shifts the treatment status. So the two instruments, we can estimate individual two-stage least squares, two regressions, and we will get estimates of these individual lates. But if we want to look at different intervals of u, like a little bit higher, for example, from 0.35 to 0.9, as the authors do in the paper, we can do that using gen late, and we've seen this last time. So we just specified both bounds of u that we're going to use. And that would correspond to having a third instrument, of course, that would affect the probability of treatment more strongly than the first instrument, the first two instruments. So, for example, if we're thinking about a new policy that could somehow affect treatment status, and we would expect that this policy would be more strong than the first two policies, Z1 and Z2, then we could extrapolate our local average treatment effect to these new values of u. Okay. Are there any questions about the fourth exercise? So I will upload this solution today, and that's what we did last time, and it was kind of a I went through this again to refresh it in your memory. And finally, if there are no questions, there's exercise 5, and this is a case when we want to compare our framework of this parametric marginal treatment effect estimation to non-parametric estimation. And of course, to do a non-parametric estimation, we need a continuous instrument because we have to differentiate with respect to probability of treatment, so with respect to our propensity score. And propensity score is, of course, dependent on our instrument. And if the instrument is discrete, then our estimates of the propensity score will also be discrete, and we will not be able to calculate the derivative with respect to the propensity score. And so I slightly changed. So last week I also added x to this mix. Then later I realized that okay, we are still going to stay in a situation where there are no covariates. It's just an instrument and a treatment status. So I removed x, and compared to exercise 4, z is now, or z is now continuous, and it is uniformly distributed between 0 and 1. And I changed this equation a bit. So now, basically, to make it a little harder, or to shift the local average treatment effect from the average treatment effect a bit. And so if z is equal to 0, the probability of treatment will be 0.5. But if a z is 1, it will shift to 0.7. And the m1, 0 and m1 functions are the same, so it's the same decreasing quadratic curve. And now, yeah, our outcome is also continuous. So we take the expected value and add the error term. And of course, the observed outcome, so these are potential outcomes. The observed outcome depends on the treatment. So if treatment is 1, then we observe y1. If it's 0, we observe y0. And as previously, we have our true average treatment effect. And of course, it's not changed because we didn't change the m1, 0 and m1 functions. So the true average treatment effect is still 0.066 and so on. And if we run OLS, again, we get this biased estimate. And of course, it's biased because people who are more likely yeah, basically, because we have always takers who have the highest treatment effect. And we can also run the two-stage least squares. And interestingly, it's pretty close to the average treatment effect, actually. But that's, again, that's a coincidence. Actually, if we look at the confidence interval, so when I ran it while I was preparing for this, I got a lower value. But yeah, the confidence interval is pretty broad here. So it should be, well, yeah, the expected value of this should be lower. And that's exactly the problem, because it's local average treatment effect. We want to estimate the average treatment effect. So we are going to use this local variation provided by the instrument to extrapolate to the whole sample. And so now we have a continuous z, and I've included all sorts of OLS estimators as in these moments, as well as a two-stage least squares estimator. And one of the OLS regressions includes the interaction term. I'm going to impose this additional restriction that the marginal treatment effect is decreasing. And we're using a quadratic specification for M0 and M1. So after we run everything, we get this result from something that's close to the true value, but the upper bound is extremely high, and it doesn't really tell us much. And so to get something more informative, we need to make additional assumptions, and the assumption I make further is that M1 and M0 are linear in U. And we've seen the true value, the true form of M0 and M1, and so this linearity assumption is not a terrible assumption to make, but of course, in real life examples, we don't know that. And so if we're interpolating to the whole sample, calculating the average treatment effect, maybe that's not such a great idea. Maybe we should change the value that we're interested in. So we could consider generalized late, which would allow us to interpolate closer to the actual changes in that we observe, the actual changes in the instrument that we observe. But here we can make this assumption, and we know that nothing terrible will happen, and the result, well, nothing terrible should happen. And again, the result is now we have its point identified, but it's again pretty off. And if we try different sample sizes or just different simulations, we'll see that these are again pretty imprecisely estimated, unfortunately. Finally, the non-parametric part, that's pretty simple. Yeah, I reduce the sample size, so I take a subsample of our original sample, which is 5,000 observations, just for it to run faster, because it takes a long time. And the first thing I do, we estimate the propensity score, and we've seen this last time, is just a logit model. But this time, in this version, there is no X. Obviously, if we have some covariates, we can add covariates, no problem. So we can add X's or functions of X's here. And we predict, take the fitted values, these are our propensity scores, add them to the data, and run our local linear kernel regression with the Panyshnikov kernel. So the first call will calculate the bandwidth for our regression. And then we can actually calculate the regression, specifying that we want to see the gradient. And the gradient is, of course, exactly what we want. It's the derivative of the expected value of y with respect to all the dependent variables. In this case, we have one dependent variable, probability, or the fitted probability, the propensity score. And yeah, but if we had x, some x's, we would include x's in the interaction between p's and x's here as well. And so our gradient is going to consist of one component. So it's a matrix. It calculates this derivative in each point of the data set. And I take the first column of the matrix, and it's actually the only column in this simple case. And so these derivatives, if we look at the textbook, individual derivatives, this is kind of this local late of x, or late of xi. The problem with this estimator is that it doesn't have good convergence properties because of this non-parametric stuff. So I'm not going to go into the theory, but it doesn't converge at a square, like n to the minus one square root of n rate, right? So it doesn't converge at that rate. And then we can't really use these as good estimates of late at each point in the data. I said xi, but actually it's zi, right? That's what we have, and di. So we take the mean, and if we take the mean, that converges under standard conditions. This is actually the only thing we can, with decent statistical properties. And then we get this estimate of the average treatment effect, but bear in mind that this number is not a very good indicator of whether our method works. I reduced the sample size because I didn't want to wait for a long time. If we increase the sample, of course, it's going to be closer to the true value. So these are the marginal treatment effect methods. And yeah, asking ambitious questions leads to either pretty imprecise estimates or requires us to make also pretty strong assumptions if we want to get something other than late from our instrument. That is, I guess, what this exercise mostly shows. And the sample size matters a lot. So any questions about the previous problem set 3? Okay, then if not, let's move on to the next problem set. It's problem set 4. And now we're going to look at instruments again, but look at covariates and lates. So basically the stuff that we had, the stuff that we had last Thursday in the lecture. And we're going to look at these two estimators. So one is the integrated late, and the other one is the late for compliers. And these two formulas are from the textbook. That's the purpose. And to illustrate these estimators, we're going to use a real life data set from the SIP survey. And let me talk a little bit about the data set. So it's mentioned in the Abadi paper as an empirical application. And the research question is the effect of the 401k program that was introduced sometime in the 80s, I think in 1985. I don't remember, but it was in the 80s. And the question is, and this program is when people save for their retirement, and it's their employers adds to the saved amount, basically, so contributes to the savings account. And the question is, people who are participating in this program, obviously, and not everyone is eligible, but those who are eligible, use this program to save for their retirement in these accounts, but does it affect other types of savings? Is there a crowding out? And we use this SIP survey, and namely the 1991 panel, one wave of this panel. And basically, we use this particular wave because there is a topical module in this survey which has all the information about all the assets of the households, or actually individuals. So on Moodle, you can see the code to create this data set. So this is the link. So you can have a look. It uses the downloaded data from SIP and also a Stata file to extract variables from this data, because it's in a fixed format, and it can be tricky, and people did some good work to write Stata code to extract variables. But then we create this sample, and the sample is the sample that I create is limited to people. Well, first of all, it's a sample of households or families. And each family has, or each household has the person who's called a reference person in the survey. And so we take these households with reference persons and aged from 25 to 64, and then we look if someone in the household was eligible for the 401k program or participated in the program, and depending on, and this is going to be our. So eligibility is the instrument and participation is the treatment. And it was shown that it's plausible to assume that eligibility conditional on some covariates is excluded. So it's or we have the conditional independence assumption for eligibility. Again, if we conditional on family income and some demographic characteristics, and the eligibility is determined by the employer, basically. And so we're going to use eligibility for participation in the program as an instrument for the actual participation and control for some covariates. And then our outcome is the net assets of the family. So we're going to, or net financial assets, I should add. So basically, this is all the assets minus debt, and the assets are financial, so they don't. I excluded the house, basically the so the data has the value of the house and the mortgage of the family, so I excluded all that. And another asset that's not financial assets, vehicles, those are also excluded. Other assets include all sorts of savings in a bank and stocks, some business assets and other assets. So we'll look at all that minus debts. And basically, this data is going to be from 1992. So the panel is 1991, but the observations took place in 1990, well, after 1991. I think it's 1992, 1993. And the idea is to compare people who participate in the program and who do not participate in the program and see how their assets differ. And again, given the conditional independence assumption of eligibility, that should give us, if we use this instrument, that should give us a causal effect of participation in the program on net assets. So basically, do people who participate in the program spend more or save more because of the program, or they don't? That's the idea. So here on Moodle, I added a link to the notebook that I'm gonna edit right now. Again, it will be updated live with a little bit of lag. So you can either watch it on the screen here or follow the link and you will see the code. You can try it out yourself. Yeah, but you will need to download this data set because we're going to use it. Let's go to the questions again. So the first question is basically question asks us to compare the means for eligible, non-eligible, for treated and non-treated, so for participating and non-participating households, and run an OLS regression. This is pretty basic stuff, so that we could compare our IV estimates to this later. And this is the descriptive statistics that we have in the Abadi paper. So he has means. So what we want to look at is the net financial assets for the entire sample, for participants, non-participants, eligible and non-eligible. The difference between what Abadi does and what I do is that here observations are individuals, which to me is super weird because the outcome variable and most of the covariates are family level, but somehow the observations are individuals. So household reference persons and their spouses. So I use data on a family level. Okay, let's start the thing. And we're gonna use some robust IV. I use the one from estimator package usually, and non-parametric methods. So reload the NP library. Now I already loaded the data. So in this file, there is one variable named D, and we can look D for data, and we can look for at the first 6 rows of the data set. And so here we have some ID, and it's called individual ID, but it's actually, again, this is household level data. So the individual is the reference person of the household. We have eligibility status, whether the household is eligible for 401k program, treated, dummy, whether the household is participating in the program. We have the age of the reference person, family size, family income, net assets, and marital status. And of course, marital status, one means that the household consists of, well, at least 2 members, and 0 means that it's a household consisting of 1 member. And so now we want to compare means and run an OLS. Let's look at the sample mean, the sample mean of net assets. Looks like I have to run this again. And sample mean is about $30,000 of net assets. And if we compare well, okay. So the data set is different, so there is not much sense in comparing to the Abadi results. But we have some average value of assets, which is 30,000 net assets, that is $30,000. Now we can just look at that by treatment status. And if we select those who are treated, we see that for the treated individuals, net assets are slightly higher than for the sample, for the whole sample. We can do the same for untreated. And they're slightly lower, obviously, since this is higher than the average. This has to be lower. And we can do the same looking at the eligibility as the eligible variable. Let's start with eligible, and then it's 31,000. Also higher than the average, but not by much. And non-eligibles, slightly lower, but again, only slightly. Finally, let's run an OLS regression. I call it MOLS. And it's OLS, OLM. Our outcome is net assets. Our treatment is treated, a treatment indicator. And we want to control for family income. Oh, age, family size, and meritless hashes. So that's the merit dummy. And let's look at the summary. So after we control for all of this and compare the treated and untreated, we see that the effect is negative actually in the as estimated by the OLS, but very imprecisely estimated. And of course, one of the problems with this data set that we're not going to really cover that much today, but which is covered in other papers, is that there is a very high heterogeneity in the amounts of assets that families hold. And so when this is, and it's also not symmetric distribution, it's a highly skewed distribution, fat-tailed, and there is a great heterogeneity. And so maybe a better idea would be to consider a quantile regression, and some authors actually do that. But we're gonna stick to our lates because that's the topic of today's class. Okay, we have this negative coefficient, very imprecisely estimated. So yeah, also it's like minus $146. So the point estimate is also pretty low, which means basically we have, or OLS suggests that there is no effect of participating in the program of the amount of net assets of the family, which means there is some crowding out, or if we believe in this OLS, there is some crowding out of other forms of savings by the 401k program. Because these net assets obviously include the 401k program. And so if the total assets don't change, then some programs have to, or some other forms of savings have to be less used than the 401k account. But of course, here we have a problem because people select into participating in the program, and maybe people who are more likely to save overall are more likely to participate, or maybe people who are less likely to save overall are more likely to participate. So maybe the true effect is different, but just the submitted variable bias makes it look like there is no effect. And that's why we need this IV. And again, the paper in which it is kind of argued that it's a valid IV is cited in the Abadi paper, is this Perturba and co-authors paper from 1995, where they look at this conditional on income and other demographic characteristics. They show that eligibility can be used as an instrument. And that brings us to question 2. So question 2 is estimate the same thing using eligibility as an IV. And first, using our simple 2-stage least squares. Let's do that, and I'm going to call it IV1. Let's actually first do it without covariates. So I'm just going to use the eligible as an instrument for treated. And if eligibility was satisfying the independence assumption without any covariates, so not conditional, but unconditional independence. So basically, if the instrument wasn't correlated with any of the covariates we have, this would give us a consistent estimate of the late, right? Okay, now the sign is different from the OLS. Will have a positive effect, but again, it's not significant. Very imprecisely estimated, standard error is way higher than the actual estimate. But let's see what happens if we add covariates. Do they matter? And of course, covariates should matter because one of them is family income, and family income is one thing that determines eligibility. So it's not that we can. So if we omit X, we're going to have the exact situation as we had in the lecture when we have to control for X, and otherwise our instrument is no longer valid. So let's include all these covariates. Add instrument using the eligible variable, and we have to include all the covariates too. So the rest of the covariates are kind of instruments of themselves. And yeah, this is the second IV. Oh. Let's look at the summary. Okay, now, after including all the covariates, we see that the sign of the coefficient flips. The effect is now negative and actually significant. Right, the p-value is, well, at 5% level, it's significant. The p-value is 0.03. And it's like minus 9,000. That's the size of the effect. But of course, here we include all the covariates as linear terms. And so the question is, the last question in this exercise, in the second part, so the last sub question and second question. Under what assumptions will this correctly estimate late as the average treatment effect among compliers? And basically, the assumption here should be that everything is linear. You can look at the theory part in the Abadi paper, but the assumption would be that first, our instrument eligible has to be, so the relationship between our instrument and all the covariates has to be linear. That's what we're assuming. But also once we've and what Abadi does in his paper, he estimates a propensity score using this instrument. And then once you have the propensity score, let's actually look at the formulas. Yeah. So first, he defines this function tau, which is the probability that z is equal to 1 conditional on x. And this, of course, is the relationship between z and x. And if we assume that this is linear, which is a bit weird, but we can use the linear probability model. And then he constructs these kappa, which act as weights in our regression. So later we run a regression that looks like this. So we model y as a function of the treatment of x's and some parameters. So basically, again, this is very similar to what we've seen in a general form in the lecture. So, but this is, we use these weights kappa, and these weights are determined by this kind of sort of propensity score here. And so if we assume that this relationship is linear, and also this function h is linear, then this will be equivalent to the two-stage least squares. So what's important, the assumptions here is that basically this regression should be linear, and the relationship between the instrument and all the covariates is also linear. And if it's the case, then our estimate here is a consistent estimate of late, defined as the treatment effect or the average treatment effect among compliers. And now the question is whether it's a reasonable assumption, whether it's actually linear. Oh, let's actually look at it. The way he controls for age is actually difference from 25. Let's do that. That I forgot. And he also includes the square of this. So obviously, as long as we have separability, we can include nonlinear functions of individual regressors or even interactions. Yeah. I just want to make it consistent with the specification. He has. Okay, so now the effect stays negative, but it's smaller and non-significant at 5% level. At 10%, it's significant. Okay, and then if we suspect that some of these relationships may be nonlinear, and why should they be linear? The probability of being eligible, that would be sort of a little bit weird for it to be linear, if it depends on these variables. So that's, again, we want to relax this assumption and look at what happens to our estimate if we allow at least some parts to be nonlinear. And that brings us to the next question. Use local linear kernel regressions to estimate the integrated late and the late among compliers. And of course, on the right-hand side, we have this late of x under the integral. And this is a formula similar to Wald formula, except we just condition on x, and it's a function of x. So for each value of our covariates, we have a local average treatment effect. And then we can just average over the sample. So in theory, is integrating over the distribution of x. But of course, the sample analog is just taking the average value of this fraction that we estimate. And we get our integrated late. But the problem, of course, so we usually think of late as the local average treatment effect among compliers, but here we integrate over the whole distribution of x's. And so we're going to average out over the whole sample. And so it's not going to be just the compliers, right? It's going to be compliers and always takers. And oh, there are no always takers, sorry, compliers and never takers. Yeah, so people who are non-eligible cannot participate. So we don't have any always takers. And so the trick is to estimate these two parts, right? So we want to estimate non-parametrically this regression, and the two in the denominator. So we split the sample according to the instrument into the 1 and 2. And this probability basically is going to be 0 because we don't have always takers. If the person is non-eligible, they will not be treated. So the denominator will just consist of the first component. So if we use non-parametric kernel methods, we can estimate 3 non-parametric regressions and calculate for each observation, for each x in our sample, calculate this amount and take the average. That would be this formula. But then the concern here could be that the denominator in some, at least in some observations, is close to 0. Well, in our case, that would be when the treatments, the probability of treatment is close to 0. And if there's a lot of such observations, then of course, this will lead to high values of this ratio for individual observations and imprecise estimates. Unfortunately, so we're going to run 3 non-parametric regressions, and so the sample size is not that large. It's like 6,000 something observations. In fact, yeah, 6,472, 71, no, 72, that's correct. Anyway, slightly less than 6,500, but it takes quite a long time to run everything. So I'm gonna put the code here, but so basically I'm gonna cheat a little bit loading the already estimated models. So I'm not gonna waste time waiting till it runs. So the first non-parametric model, let's call it MNP, and let's call it 1. Let me write what we're gonna estimate here. So estimate E of Y conditional on x equal to x and z equal to 1. And that's one component of our formula, this one. And we're gonna use our NP package, which we've seen already multiple times, and a local linear kernel regression. And for that, we need to first calculate the bandwidth using cross validation, and it's done by this npreg bw function. And so again, our outcome is net assets. And now we need to include these variables here. So legible is our z, the rest are components of x. Well, we don't need this term anymore. It's non-parametric, non-linear, so let's just put age. Now, before this could be run, we need to tell R that married is a dummy variable. So it has to know that married is a dummy variable. And so I convert it to a factor. What else? Yeah, and of course, we need z to be equal to 1. So we're going to use the subset argument. So this is a logical vector, which is true for the observations that we include and false for the observations we exclude. And we are going to include only those observations that are legible. Now we want to run a local linear regression with Konechnikov kernel. All right, and also our bandwidth method, we're going to use cross-validation using least squares. So after we run this, we can actually run the regression. So let me call it bandwidth. And the actual model is fitted by the npreg function. That's our non-parametric specification for this question. So we are going to do the same for the non-eligible. And now for the denominator, let me call it P. We just specify, so it has to be 1 because the probability of being treated for non-eligible people is 0. And here we have treated. And of course, treated is binary, but we'll see how it performs and compare to, say, logit. Sorry. Let me rename the variables so that they're named the same as I named it in my file. So this should be bandwidth M0. It's the other way around. And NP M1 bandwidth M0 and NP M1 M0, sorry, bandwidth P0, sorry, P1, and and P1. Okay, so now this will correspond to what I'm going to load. So let's imagine that I ran it, and let's get the result. Great, it didn't crash. Okay. Now we can look at the results of our estimation. Let's look at the bandwidth of model 1, for example. And here we have the bandwidth. By the way, yeah, I wanted to divide family income into. Okay, that doesn't really matter. So we have our estimates for the bandwidth. Actually, for the merit variable, it's almost 0. So basically, it turns into a matching estimator for this variable. So it's going to match on this variable, and we have some bandwidths here. And what we can do with the model, we can plot some graphs and see if they're nonlinear. So let's plot NPM1. Oh. Okay. So what's plotted here is the graph for individual variables holding other variables at their means. And we see that the relationship with the family income is actually pretty nonlinear. Also, there is a nonlinear part of this H variable, and we have some nonlinearity in family size. So our linearity assumption wasn't a good one, or certainly seems from these graphs. And of course, the nonlinearity can be even worse for more extreme values of other variables, because we plot these graphs for mean values of age, family size, and merit. Yeah, if we look at the other graphs, so let's plot the other one, 1 hertz for M0. So here again, we see some nonlinearity in family size, but the nonlinearity in family income is less pronounced. And let's look at what our propensity score looks like. So for P1, yeah, and here we see a very interesting, peculiar form of the function regarding family income and family size. Since we don't extrapolate like anywhere beyond 200, family income being less than 10,000 and 200,000, we won't get any probabilities or any values of the outcome, which is a probability greater than 1 or less than 0. But and we limit, our sample is limited to values of family income between 10,000 and 200,000. But here on the graph, we already see that the probability doesn't go far lower than 0.5. At least for, again, we will examine the whole sample, but it doesn't seem that it goes close to 0. Or maybe it does, we'll see. Not in this graph. It definitely goes closer to 1 for high income families, which is kind of the point of why we have to control for income. Okay, let's have now a logit model instead of the non-parametric specification we do, and compare our probabilities to the logit model, just out of curiosity. So here I'm gonna again quickly do this. Since we have a parametric specification, and we want to logit, and I want summary of that, just in case. Yeah, I forgot to say. How about now? Yeah. Okay, so here are our coefficients. We see that higher income families are more likely to be treated. Higher people of higher age are also more likely to be treated, but that is slightly nonlinear. So the first derivative is decreasing, and the larger the family size, the less likely the families to participate, and married people are more likely to participate, or married families. I mean, families of more than one people, basically. Yeah, but the point is to actually look at the predicted values. So yeah, so if we plot the logit fitted values, so on the horizontal axis, we will get the predicted probabilities from logit, and the vertical axis, we're going to have the probabilities from our non-parametric model. And of course, it's fitted. Okay, and let's add basically an x equal y line to compare it to it. Why don't I see it? Oh, sorry. The intercept is 0. Yeah, so we see that a lot of, let's make them transparent. So to see where the mass of the points is, let's make them slightly transparent. So yeah, I think this is okay. Yeah. Now we see that the most of the mass of our observations are along this line. So our non-parametric estimates are pretty close to the logit estimates. There is some, there are some differences, of course, and there are some more extreme values. But we see again that our non-parametrically fitted values, non-parametric probabilities, don't go really that close to zero, except in one observation. So something happened here. Other than that, they're pretty close to the logit ones. But of course, due to nonlinearity, there are some discrepancies. I mean, the nonlinearity of the linear index is the logit. So logit is also a nonlinear model, of course, but it has a linear index in it. Okay, but that's not what we're interested in. I mean, that's just to see how our model performs compared to some benchmark. Now we want to calculate our late estimate. Let's call it late 1 or late integrated late. And so we will need to take the mean of a fraction. And in the numerator, we will have our fitted values from a model for expected values of y conditional on z being equal to 1 minus same thing for z equal to 0. And in the denominator, we have our fitted values from the model for probability for treatment or expected, which is the same expected value of the treatment status. Oh, sorry. This will give us no. Obviously, we estimated the model. If we take just the fitted values, it will be fitted only for those values of z for which we estimated them, but we need to predict them for the whole sample, of course. So we need y1, and we use the predict function, and we use our non-parametric model 1, and we predict it for the whole sample. Same goes for y0. And p1. And now our late integrated late is the mean. And now it's going to be the whole over all of the observations of y1 minus y0 divided by p0, 1. And yeah, I need to print it. And our estimate is minus 2027, roughly minus 2600. So this is the integrated late. It includes, unfortunately, it includes not only compliers, but also never takers. Since we integrated it for the whole over the whole sample. And maybe that's not what we want, maybe because it's kind of hard to interpret. Maybe we want to see something we're more familiar with, or yeah, more used to, is delayed for compliers. And that's the next question. And basically, what needs to be done here? Well, first we could just, one way to estimate is just to take average of the numerator divided by the average of the denominator, or we could not just do that, but also add these yi's as basically another estimate of the m0 and m1, and the i's is another estimates of these two quantities. So this is the formula from the textbook. And yeah, this is the estimate of the late among compliers. And so basically it's not integrating this whole fraction. It's kind of integrating the numerator and the denominator separately. We have already everything we need to calculate it. It's just and again, it's a fraction. And then the numerator, we have a difference between this quantity for observations where z is equal to 1. So I'm going to use the if-else function. Oh, and just to avoid typing d everywhere, I'm going to temporarily attach it here. So if else are eligible, this is our z is 1. I'm going to take y, which is net assets, sorry, predicted y, which is y, no, sorry, everything right. So actual observed y minus predicted y, and minus predicted, predicted y for minus m0, basically. So minus y0. And I'm going to take a sum of this. And something's not right. Yeah, and this won't work unless. Okay, minus a different sum. Now we look non-eligible, and here use y1. And in the denominator, we only have, okay, here we're going to have two components because di's are observed. So the first one will be sum of the di's for which z is equal to 1. And these are, of course, are treated variable, but are eligible equal to 1, treated otherwise 0, minus something very similar, but we'll need to subtract p1. Eligible should be 0. And I have more parentheses that I should. Oh no, it's fine. Okay, let's hope it is correct. Okay, it doesn't, it calculated something. And if we take late for the compliers, we're getting this result. Minus 22,452. So it's pretty close to the integrated late, as it turns out. Now, just to recap, to see what we have in other, for other estimators, we had two. So again, we have our OLS model in which the estimator is almost zero, so very low and but positive. And we have our IV like linear IV model. It gave us a negative value, but pretty high. Well, higher than we got using our late estimates, but this wasn't significant. And so accounting for this non-linearity actually leads to smaller estimates. And of course, we could calculate and look at the standard errors for these estimates, and then have a standard error for this, or a confidence interval for this late estimator. It's probably statistically not significant. But we see that if we assume, or if we believe that our instrument is a good instrument, the conclusion would be that participation in the 401k program actually does, if it does crowd out other saving methods of saving, it doesn't do it like by a large amount, right? So the effect is slightly negative, the point estimate is slightly negative, but it's statistically not significant and quite imprecisely estimated. So that's it for the late. And of course, we see that in this case, it is important to control for the x's. First, because our independence assumption is for the instrument is satisfied only conditionally. And secondly, due to these non-linearities, yeah, our non-parametric methods give somewhat different results, but not very tremendously different in this case. So the linear case is the linear IV is a more or less decent approximation. Any questions regarding this data set? Okay, so if there's no questions, then I'll stop the recording. If I find